I know we did 1 through 3. You guys, homework was to finish 4 through 6. I feel like number 4 is pretty straightforward in terms of, we've seen these problems like this where we're given a derivative graph and we're asked to find information about the derivative graph. And then this is page E, by the way. Find the absolute max and min. We should be able to recognize, oh, this is a need for EVT. And I did a help session this morning talking about how, if they give you a formula where you can find the area, then use that formula. But if they don't give you a formula and you're given the f prime graph and they're asking about specific locations on the f of x graph, you're gonna have to go through this final equals initial plus displacement formula to move your way through finding your points. And then the rest of it is just finding all the endpoints using EVT, extreme value theorem. I think number 5 is pretty straightforward in terms of, if we recognize chain rule and product rule, we can just build them out. I think number 6 is a little tricky, or maybe it's just ones that we haven't quite done as much of, and just want to point those steps out. So this is page H and I here. It says, starting with this equation, find the derivative. We know we want to go through product rule and implicit. So we're starting here and we're building out to this derivative. So when it says show that dy dx equals, that means this is where they want you to end up, but this is where you're starting. Okay. And then part B and C says find the coordinates in which the line tangent to the curve is horizontal versus find the coordinates in which the line tangent to the curve is vertical. So whenever you're finding a horizontal tangent, that is basically asking where the slope is 0. So if I want to find where slope is 0 off of the derivative function, I'm going to be looking at the numerator. We're going to set the numerator equal to 0 whenever you're doing a horizontal tangent. Now, anytime you're looking for a vertical tangent is where the slope of the graph is undefined. And if the slope is undefined, you're going to look at the denominator. You're going to set the denominator of the derivative equal to 0. So we haven't, we've done those before, but we haven't seen those as much. And then so parts B, you're setting the numerator equal to 0 of the derivative. Part C, you're setting the denominator equal to 0. But saying the denominator equal to 0 doesn't quite get you down to a number. So you have to take that, insert it back into the original equation, go through substitution and solve for one variable, and then go back and solve for the other variable. This is a little messy in terms of the algebraic steps involved. And then part D, we should be able to recognize, oh, this is related rates because I see a bunch of d over dt's involved. So I'm going to find the derivative again, but instead of dy over dx, I'm going to have dy over dt and dx over dt. So I'm still going to go through product rule, but instead of implicit for dy dx, now I'm going to have related rates for dx dt and dy dt. And then once I have all those variables in front of me, then that gets easier. Then it's just plugging information that the problem gives you, and then just trying to solve for the missing variable that they're asking for you to find. Okay, any questions from the 2023 FRQs? Okay, so today we're going to work on the 2022 FRQs. I'm going to highlight problems for us, and then whatever we don't finish will be your homework. Okay, let's start with number 1. This is page 1 here. Start with letters A through I, and now we're down the page up to page 1. Okay, so this is number 1 off of 2022. Again, we know 1 and 2 are calculator active problems. 3 through 6 are non-calculator problems. Okay, so from 5 a.m. to 10 a.m., the rate at which a vehicle arrives at a certain toll plaza is given by A of t. This is a rate, keep that in mind, where t is the number of hours after 5 a.m. and A of t is measured in vehicles per hour. Traffic is flowing smoothly at 5 a.m. With no vehicles waiting in line. Write but do not evaluate an integral that gives the total number of vehicles that arrive in the toll plaza from 6 a.m. to 10 a.m. Well, if I have vehicles per hour, I can use the integral and get that vehicles per hour up to the total number of vehicles, right? So part A is pretty straightforward. You're just doing depth integral from 1 to 5 and just entering that into your calculator. Actually, we're not even solving here. We're just setting it up. So part A, we're just setting it up. So you can write out the entire expression, or you can leave it as A of t. That's it. That's all we do, number 1, for part A. Part B, find the average value of the rate. So average value theorem, right? So again, easy calculator setup. If we know what the formula is, we just have to put it into our calculator. Average value theorem, 1 over b minus a. My a is 1, my b is 5. So 1 over 5 minus 1, integral from 1 to 5, integral of a of t. Insert that into your calculator, math 9, and the average value. So it'll be vehicles per hour. It'll stay as vehicles per hour. Part C is the rate at which the vehicles arrive increasing or decreasing. So we want to know, is the rate increasing or decreasing? This is not just looking at A of t, this is looking at A prime, right? We're asking about the rate of change of A of t. So we can just find A prime of 1, do math 8, see if that will get you a positive or negative number. Okay. Positive number would mean that the rate is increasing. Negative number would tell us that the rate is decreasing. And then what's our unit going to be for A prime? Yeah, the vehicles per hour squared. Yeah. Okay, so since our A prime is positive, we know that the rate at which the cars arrive at the plaza is increasing, equals 1. Part D, a line forms whenever A of t is greater than or equal to 400. So that means the line forms whenever the rate at which cars are arriving is more than 400 per hour. It's going to starting to get backed up. Okay, so number of vehicles and time between A and 4 is given by this n of t, where A is the time in which the line first begins to form. The nearest whole number, find the greatest number of vehicles in line between A and 4. So here, yeah, we know that this minus 400 would indicate if it's less than 400 that it's good, but once it gets 400, it's going to start backing up. And this is going to tell us, n of t is going to tell us the number of vehicles that's going to form that line. Okay, so anything we see this greatest number of vehicles here, what does that remind us of that we're going to be applying what theorem?
EVT.
Yeah, anytime we see absolute max, absolute min, greatest, smallest, right? Any of those extreme values, we're going to be applying EVT. So we know we have to find critical points. Now, endpoints is easy to identify, right? Endpoints is just going to be between A and 4. And we're going to have to maybe use our critical points to actually use that as endpoints. So we know it's going to be t equals A, which we're going to find later, and t equals 4. Now, to find critical points, what do we need to do? We need to set the derivative equal to 0, right? So critical points is set the derivative equal to 0. So we have to do some work finding these critical points. So let's find n prime, and from n prime, we can find the derivative. So here's n of t. Sorry, dx. If I want to find the derivative, n prime, I know I have to do d over dt. Or d over dx of the integral from a to t, a of x minus 400 dx. Okay, so we know that if I find the derivative of definite integral, we know these operations cancel each other out. What's left over, though? Just the bound, right? The a is just a number, there's some constant, but t is a variable, so we can insert t in for x. So n prime, it's just going to be a of t minus 400. Okay, so now that we have our derivative, we can set this equal to 0. So 0 is equal to a of t minus 400. Okay, so just like how these problems are difficult to solve by hand, but this is meant to be a calculator question, so we can graph this and then look for the x-intercept. So let's try that. So here's my a of t, 50 times the square root of sine of 0.62x minus 400. I'm going to adjust my window a bit. I'm looking at here between a and 4. So it's got to be, my x values is not going to be more than So I'm going to just say from like -4 to 4 or -5 to 5. I can. And then my Ymin and Ymax, if you look at your coefficients here, these are pretty large numbers, right? All the way up here and in the 500s. So I like to just kind of match that number here. I'm going to say from -500 to 500, just so I can start off by having some, because I know that with such a large value, I need to zoom out a bit. So I'm just going to see what that graph gives me. Okay, so now I know I'm looking for my x-intercepts. So I can do second trace, 0. So pick a point to the left of the x-intercept, hit enter. Pick a point to the right of the x-intercept, hit enter. 1.469. So that's one x-intercept, second trace. So we know that the line is going to begin to first form whenever n prime is equal to 0. So we know that's going to be our starting point, and then our ending point is going to be 3.592. Well, 3.598, but then they say the ending point is also at 4. So we're going to test those values. So we found our critical points, 1.469. That's when the line begins to form. And then we'll test 3.598, and we'll also test 4 because that's our other endpoint. So between those points, we just plug into our n of t. So our n of t is just the integral from 1.469 to whatever endpoint we're looking for. We know from 1.469 to 1.469, there's going to be just 0 because our bounds are the same. And then we can test 3.598 in our calculator. And we can test 4 as well. And between these three, we can see that 3.598 has the most number of cars backed up. So the maximum value of n on the interval from 1.469 to 4 is 71 cars. Okay, let's look at number 2. And number 2 is also a calculator. Okay, number 2 says, let f and g be the function defined by f of x is natural log of x plus 3. That's the graph that's higher. And then we got x to the 4th plus 2x cubed. That's the one that has more of these curves here. So that's the one that's below. And then the intersection is -2, and then this unknown, well, we have to find it on our own with our calculator, find that intersection. And then we need to find part A, find the area of the region enclosed by the graph of f and g. So we can plug this in our calculator, and then we can use our second trace intersect feature to find that x value of our intersection. We can do top minus bottom. We always want to try top minus bottom first for area, and then if that doesn't work, then our last resort is right minus left. But we should always try top minus bottom. Here, the top function is clearly the natural log. The bottom graph is clearly the x to the fourth. So we can just do area is just integral, definite integral from -2 to, and we find that intersection ends up being 0.782. And we just do top minus. Now, I think area formula is easy, but having said that, if we do volume formulas enough, like washer and disk method, we may be tempted to want to do and just add things to the formula that's not part of the area formula. So sometimes I see students involving pi. Sometimes I would see students involving squared. Okay. I know area, typically we square things, but this is the top minus bottom is a one-dimensional, it's the height component. The dx is the width component. We don't have to add any more square to it. Okay, so the squared is for disk and washer method, but for area, it's just top minus bottom. We don't square anything. It really is as clean, as simple as that formula. Okay, so okay, so our top function is natural log of x plus 3. Our bottom function is x to the fourth plus 2x cubed. If it helps, maybe you want to call this graph it under y1, graph this under y2, and then do math 9 from -2 to 0.782 and do y1 minus y2 dx. Okay, part B says between -2 and b, which we found as 0.782, let h be the vertical distance between the graph of f and g. So the vertical distance is just this minus this, right? So we're going to build that vertical distance between f and g and just call it f of x minus g of x. Vertical distance. So now that we have our vertical distance equation built, it says, is h increasing or decreasing at x equals -0.5? So if I want to do anything about increase, decrease, am I going to be talking about h, or am I talking about something else? If I want to find rate of change or increase or decrease, I have to get to what? H prime. So h prime is simply f prime minus g prime. And then we can just plug in -0.5 and see if the f prime minus g prime is giving us a positive or a negative number. If we get a positive number, we know that the vertical distance is decreased. If it is increasing, if we get a positive number, we know the rate of change, the rate of increase, the distance is increasing. If we get a negative number, we know the distance is decreasing. So all this is calculator work for us. We can just math 8. Say, can I say, yeah. 5 different things we want. Right, so again, we have our f function, we have our g function. So if we do math 8 for -0.4 f, and we can do math 8 for g, we can get to that number there. And then negative number indicates our vertical distance is decreasing. Part C, the region enclosed by the graph of f and g is the base of a solid. Cross section perpendicular to the x is squares. So we're doing a volume problem with cross section. So we know that we can find that vertical distance. It's just going to be f of x minus g of x. That's our base length. And then once we get our base length, we know that we're going to build squares. So the formula for squares is base squared. And once we have our area formula for base squared, we put the integral around it to give it that third dimension. And then the rest is the calculator work. All right, part D. A vertical line in the XY plane travels from left to right along the base of a solid described in part C. The vertical line is moving at a constant rate of 7 units per second. Find the rate of change of the area of the cross section above vertical line with respect to time when the vertical line is at position x equals negative 0.5. So there's some context clues, right? We see units per second. We see with respect to time. What does that remind us of? That we're going to be applying what? We see time mentioned here, so what derivative process? Something else. What has a bunch of time components in our derivative? Rates. Related rates, right? So typically, this is what we've been seeing over the years is that there's less and less problems that's devoted to related rates. We're probably not going to see a full related rates problem, but what they like to do now is to insert a related rates problem into like a part C or part D of a problem. So, look for that, right? So anytime you see time components, with respect to time, where they give you information about, things like moving at a rate of 7 units per second, that's indicating that, okay, well, they're probably wanting us to apply related rates in some form. So we want to find the rate of change of the area. So we want to find dA dt. So we know the area that we built from above is f of x minus g of x squared. So that's our area. And if we want to find the derivative, I know I got it at dA dt showing up. I'm going to have dx dt show up as well, since those are the two variables at play here. And we have to also recognize, oh, this is also chain rule as well. So, this is part D of an FRQ. So I would say this is kind of a bit more challenging in terms of the setup, right? First, identifying that, okay, this is an area. We got to build that area from part C. We have to recognize this is a chain rule here, outside times inside derivative. So outside portion is that bracket squares. So it's 2 bracket to the first power. Inside derivative, f prime minus g prime. And then we're asking for x's derivative. So I also need to include dx dt. That's a tough, yeah, there's a lot going on, right, to build that derivative. But that's the hardest part, getting to this derivative, and the rest is just plugging in, right? We know that we're going to replace every x with negative 0.5. We know dx dt is 7, and then we should be able to make our way down to a numeric answer, which is dA dt. Okay, number 3. So number 3, let f be a differentiable function with f of 4 equals 3. The derivative graph is given. Find f of 0 and f of 5. So if I want to find a point on the function not given the derivative, either they give me a formula or I have to use final equals initial plus displacement. In this case, they don't give us a specific formula to use. So we're going to use that final equals initial plus displacement as our way to move through the problem. Okay, so here's my formula. X of b equals x of a plus the integral from a to b of x prime of t dt. Okay, so it says find f of 0. Okay, well, first, I'm just going to go ahead and see if I can label as much of the graph as possible. I know my semicircle is a 1/2 pi r squared. I got a small triangle here, 1/2 base times height. I got a rectangle here, 2, and I have a triangle above at 1. So if I want to find f of 0, I know my anchor point is f of 4, so I know I've got to go from 4 to 0. I know our tendency is wanting to go from 0 to 4, but when you write your final equals initial plus displacement, make sure that you're matching your starting point with where you're coming from, right? So this is my starting point. I need to start here and end here. That's what I'm going to put on paper to begin with. But if you're having to read the graph from there and you want to flip the bounds, you can flip the bounds later. But when you build your formula, follow what the formula says. And then if you realize you would prefer to flip the bounds, which in this case, I prefer to flip the bounds, I'm going to do that and then change the signs. Okay. And now the area or the displacement from 0 to 4 is going to be the semicircle, triangle, triangle, and the, to 4. From 0 to 4. All right, just a semicircle. So just -2 pi because it's below the x-axis. So I'm starting at 3 and I'm going minus the -2 pi, which becomes 3 plus 2 pi. And if I want to find f of 5, again, my anchor point is f of 4. And now it's at the bridge the gap between 4 and 5. Now 4 and 5 is already in the order from left to right. So I don't have to change the bounds. Just have to read my graph here from 4 to 5. That's just an area of 1/2. So 3 plus 1/2 to 3.5. Part B, find the x coordinates of all points of inflection. So how do I find points of inflection if I'm looking at the f prime graph? Yeah, peaks and valleys, lowest and highest, the max and mins, right? The relative max and relative mins. So we know there's points of inflection at -2. We know there's points of inflection, sorry, at 2, and there's a point of inflection at 6. So we can say POI occurs there because f prime, which is our graph, changes from increasing and decreasing. Part C. Let g be the function defined by f of x minus x. On what interval is g decreasing? So we know that anytime it's asking about decreasing, increasing, we know that's rate of change. Rate of change, we got to get to g prime first. So we'll get to g prime and look to see is g prime ever negative on the interval from 0 to 7. So we can just go through first derivative test. So we'll find G prime, set G prime equal to 0, find our critical points, and then we'll test each subinterval. So my G prime is just F prime minus 1. F becomes F prime, X becomes 1. I set G prime equal to 0. I find that my critical point is at 1. So, or F prime of X equals to 1. So if that's my critical point, I got to look at my graph here. Where's my F prime equal to 1? F prime is equal to 1 at 5 and at 7. And my endpoint is at 0. So really I have to figure out whether my G prime is positive or negative. So if I plug 1 in, F prime of 1 is negative 1. So negative 1 minus negative 1 is negative. So I know that region is negative. If I plug 6 in, F prime of 6 is positive 6 or positive 2. 2 minus 1 is positive. So I know that there is a decreasing interval from 0 to 5. And part D, absolute minimum, we know we're going to be doing EVT. So we set the test 0, 5, and 7. Using final equals initial plus displacement and compare the Y values. Highest Y value is our absolute max, lowest is our absolute min. And this is without a calculator here, number 3. So if you don't know what 3 plus 2 pi is, just do an approximation. You know pi is around 3, so 3 times 2 is 6, 6 plus 6 is 9. That's obviously more than negative 0.5, 1.5. So between these 3 values, lowest Y value is negative 1.5. Okay, let's see if we can just spend a few minutes just to start number 4. Okay, so number 4, we have an ice sculpture. We have a table of values. This is Riemann sums here. Approximate R double prime of 8.5. You know that R prime is given to you. R double prime is the slope or the rate of change of R prime. So we can just find slope. So find the closest order pairs to 8.5 and then just do slope of R prime divided by the slope or the change in R prime over the change in prime. And then your units of measure will change from centimeters per day to centimeters per day squared. Part B, is there a time between 0 and 3 such that R prime is equal to negative 6? Well, the nice thing is that this is we have R prime table in front of us. We have value below negative 6 and we have value above negative 6. So this is a easier problem. There's no need to do mean value theorem. IVT can get us there because we can clearly find R prime below negative 6 and R prime above negative 6. So we can say by IVT, because R prime of 0 is below negative 6, negative 6 lands cleanly between negative 6.1 and negative 5 on my table of values, then there must be a time where R prime is exactly negative 6. Part C, write Riemann sums. So we do width times height. We want to keep all the negative values. So that negative 51 tells us that the ice sculpture is decreasing in size or has decreased by 51 centimeters over the course of that 12 days. And then part D, we see all these mentions of time. So anytime you see with respect to time, you got to think, okay, maybe they're trying to get us to use related rates here. So for part D, you're going to do product rule and being able to build out that derivative, get the dBdt to show up, get the rdt to show up, get the hdt to show up, and then use all the values that they provide for you to get it down to a number. Now, keep in mind, this is non-calculator, so this is a mess of an answer, but there's no need to clean anything up, right? So if it's non-calculator, they're never going to expect you to clean anything up. So as long as you get it down to the numeric answer, if everything is a numeric value, leave it alone. Don't try to clean any of that up. Okay, so tomorrow I'll be checking your 2022 FRQs, and then we'll briefly go over that tomorrow, and then we'll go to 2020. Get your phones. Just want to, if you got it, probably. Thank you. Yeah. Oh, okay. Okay, thank you. Then have you finished the stay? All right, show me you can. Oh, that's what I confused. 2023. Good sense. You can like, do you want to like presentation like? Yeah, I'm going to most recently. I'll show you both the 20 but if you want to. Okay. I'm also doing sessions every morning.
Sorry, today I couldn't do it in the morning because I had fires. Yeah, like today and tomorrow I'm doing this microeconomics B session.
Okay.
Because we haven't like taken my classes first semester. Maybe Friday morning or Thursday morning. Yeah.
Okay. So they will try. So it's Friday mornings. Yeah. Oh, that's okay. Thanks, guys. Have a great day. Hi, thank you.
Nobody else.